Morning, everyone. I'm Kenan Zhang. I'm currently a postdoc at ETH, working on topics at the intersection between transportation, control, and learning. But this presentation I will present today is based on two studies that I did during my PhD at Northwestern. So both of them have the objective to learn individual behaviors from vehicle trajectory data. So I think one of the most important technology development in the past decade is this mobile computing and communication. And along with this rapid growth is the great amount of digital footprints derived from our personal devices. And among the data sources, the vehicle trajectory data is perhaps the most widely available. And in the literature, this type of data has been used in a wide range of research. So first, because this vehicle trajectory data contain rich information about the trip origin and destination, people have been using that to construct the urban mobility profile. And similarly, we can use this data to detect the communities and the hotspot in the city based on the aggregation and segregation of these urban trips. And also vehicles with this GPS devices are great sensors of the urban traffic. So there are a lot of research showing that with high frequency GPS data, we can very well predict the short-term traffic. And another interesting application is to use the historical trajectory data to do the location and route-based recommendation. For instance, one application is to suggest the taxi drivers to do the recommend search location or search path to this taxi drivers based on the pickup and drop-off pattern. So all of this research have remained at the aggregate level, but in this presentation, I want to focus on the analysis at the individual level. So this is the outline of my presentation today. I will first introduce the data we use in these two projects and some pre-processing steps. And after that, I will present the two projects. The first one is basically learn the behavioral pattern from the trajectory. And the specific application is that we want to recognize some the passenger search strategies of taxis from their historical trajectory. And the second project is all about learning the latent state in the trajectory. And the specific application is to correct the mislabeled occupancy state in the taxi trajectories. And finally, I want to discuss some main challenges and the trade-off when I did these two projects. And I'm also really appreciate your feedback and comments. So now let me first introduce the data set. So the data we use for these two projects are the taxi GPS trajectories collected in Shenzhen, China. So this snapshot present how the data look like. For each GPS point, we have the taxi ID, the timestamp, the coordinates, the instantaneous speed and orientation, and finally the occupancy status, which indicates whether there is a passenger on board. So in this particular example, we can learn that this taxi has been waiting at a certain location for a while because it has zero velocity, and they remain at the same location. But then the taxi pick up a passenger and start the trip. So for both two studies, we did some pre-processing process. The first one is to augment some geographic information to each data point. So basically, we map each GPS point to the TAZ and also map each point to the road segment. The second step is to do trip segmentation, basically using the information of the occupancy status. And the third step is to do a hotspot extraction. So as you can see in the top figure, most of the taxi trips are concentrated in certain part of the city. So we use a variant of the DB scan algorithm to detect the hotspot. So because the trips are not uniformly distributed in the city, if we just simply use DB scan, then we can get a really large cluster at the lower part of the city. So this the algorithm we use can adaptively change the neighborhood size and the points in each cluster so that we can identify hotspot in the city center. So now let me introduce the first projects we did using this trajectory data set. So the main problem here is to identify different search strategies among individual taxi drivers. So in the literature, this problem has been tackled in different way, but a common approach is to first pre-classify the driver group based on their performance, for example, the hourly earning, and also predefine some search strategy as shown in the bottom plot here. And there are also related work on this topic. One is to model drivers are as the rational agents in the market with full information about the market condition. And the other one is just to design the optimal search path for each driver based on the historical data. So different from this work, in our study, we really want to directly learn the taxi search behavior from data without any prior knowledge about their class, their strategy, or whether they are rational or irrational. So our approach is to develop this image-based representation of individual behaviors. So essentially, we draw an analogy between the behavior, spatial temporal behavior, to an image. So in this image, each pixel has a spatial temporal index. So we can put the feature of each search strip into this image, and each feature map can correspond to one channel in this image. So this diagram shows how we construct this image representation, which we call hunting image in this study. The following several slides shows how we define the features used in this study. The first two are cruising speed and cruising ratio. We believe these two features imply the search strategies of drivers. For instance, in the two figures here, in the left figure, the taxi basically cruise locally at a relatively low speed, while in the second figure, the taxi directly go from the airport to the sub-center after dropping off his last passenger. So it leads to a trip with a high speed and low cruising ratio. The next feature defines how much the search is driven by the demand and supply pattern. So We first normalize the demand and supply by location and time and compute this demand-supply ratio. And finally, we define this difference in supply-demand ratio as the difference of this log demand-supply ratio. And finally, the final features we use is the distance of the next passenger trip. And we believe drivers really have a preference where they find the passengers. So some drivers prefer to go to transportation hub like train stations because passengers there tend to have a long distance trip, while others just cruise in the city center trying to pick up as many passengers as possible because then they can finish the many trips within the same period of time. And this figure also shows that this preference can vary over time and vary among taxis. So that's why we also choose this feature in our study. So now we have our features and have our hunting image. The next thing is to recognize strategies among taxis. And the problem here is essentially to identify a low-dimensional structure embedded in a high-dimensional feature space because the hunting image really have a high dimension, really has a high dimension. And the idea of this sparse space clustering is to represent each taxi as a sparse linear combination of others. So in the formulation, we have the feature matrix Y and the representation matrix C. And the regional formulation is to minimize this L1, L0 norm with this equality constraint. But the L0 norm is very hard to solve, so this formulation is relaxed to a L1 norm, and further we add the outlying entrance to Z to further relax the equality constraint. So this slide shows how we solve this sparse space clustering problem. So we first write it into a more compact form and replace the X in the objective with the B and add additional constraint to ensure the equivalence. Then we can apply the ADMM algorithm to solve this sparse coding problem, and the iterative rules are shown in the slides. So after we have this sparse representation matrix C star, we need to do several more steps to recognize the patterns in the hunting image, which is essentially the spectral clustering and the representation matrix. So we first normalize the representation matrix by column and balance that so that we have a symmetric matrix, and then we do the k-means clustering and normalize the graph Laplacian constructed using the balancing matrix. And here the cluster number, in theory, is determined by the number of zero eigenvalue in this graph Laplacian, but in practice, because of the data noise, we don't really have a zero eigenvalue. So I will introduce later how we determine the cluster number. So in this experiment, we choose around 900 taxis, which continuously operate in the analysis period, and also have at least, each of them has a list of 450 valid search trips. So then we construct the hunting image for each taxi. and the time horizon is represented by this half-hour intervals, and for the space dimension, we discretize the search distance and use the percentiles to represent each slot. And so for each pixel, if we have multiple trips, we just take the average value for that specific space-time slot. So this slide shows the original hunting image we have. As you can see, the dark blue parts are all empty slots. So to deal with this data sparsity, we do some Gaussian filtering and max pooling, which is a common image processing tool, so that we can reduce the dimension, fill the image, but still retain the main patterns in the image. And the figure on the left bottom show the eigenvalues, the ordered eigenvalues of this normalized Laplacian. And as you can see, with different iterations of ADMM, we always have a significant jump at the 24, so we just choose 24 as the clustering number. So because the cluster number is really large, I can only briefly show the main patterns of the largest taxi clusters. And the figure here shows the average hunting image for each cluster. So at the first glance, you may find their feature distribution are very similar. And also, we can identify particular time windows where the features change a lot. And also, like for the short distance search trip, the distribution are very similar. This is expected because these vehicles can hardly start their searching process before they pick up their next passenger. But these figures also show interesting patterns that is different among clusters. For example, we can identify drivers who prefer direct search with a high speed and a low ratio, but there are also passengers prefer the local cruising with a low speed and high cruising ratio. And also, some drivers are shown to prefer a long distance trip, so particularly for the after a mid and long distance search. And others prefer short distance trip during certain time period of the time. And finally, we can find some drivers who are really good at find locations with high demand and supply imbalance at night, so they can have a higher probability to pick up passenger when the demand drops at night. Okay, a summary of this first study, I think we propose an image representation of individual drivers. So I think this idea is quite flexible and can be used in different behavior analysis. And also, once we have the label, we can use more well-developed model for computer vision to analyze the behaviors. I think another main takeaway could be when we analyze the behavior, we want to use full information from the data. So one approach is to first expand the feature space and then do subspace clustering so that we can make full use of the information while avoiding the curse of dimensionality. So the next project is to do a correction of the occupancy status in taxi trajectories. As I mentioned, when we do the trip segmentation, we mainly rely on the occupancy status. This normally works well, but when we have a noisy data in this particular column, it causes serious problem. For instance, in this figure, we can see there are several flips in occupancy during this segment, and here we use different color to represent the occupancy and also plot the mark size is inversely proportional to the vehicle speed. So that means this vehicle is moving at a high speed while changing its occupancy. So if we further looking into the road mapping result, we found that this vehicle is actually moving on highway. So it is impossible to pick up or drop off passenger. So this arrow cannot be fixed by simple filtering because this mislabeled segment is relatively long. And also these errors could cause a serious problem because it basically mislead the distribution of trip and also the trip origin destination. So in the machine learning community, this similar problem is always formulated as this learning with label noise. And there were three general approaches to solve this issue. The first one is do the data cleansing, which basically detects the abnormal data and remove that. And the second one is to use model or loss function that is robust to this data noise. The third one, which is also used in this study, is to incorporate the noisy data into the model framework. So before I present the formulation, I'd like to formally define the problem. So the input of this problem is trajectory sequences, which is a series of, which is a set of series of GPS records, so, where the time difference between two consecutive points is less than a threshold. And we also define the occupancy transition as the a change in occupancy between two consecutive points. And we then define the taxi state, which is unknown, and it takes value from this vacant, pickup, occupied, and drop-off. And finally, we define the features, which can be classified into two groups. One group is input feature, which are independent but affects the taxi state. And the other group is output features, which are dependent on the taxi state, like the vehicle movement. So the main objective of this problem is to predict the true taxi state sequence based on the observed input and output features. So we cast this problem into this input and output hidden Markov model. Here we assume the taxi state at each time step only depends on the previous state and also the input features. And given the taxi state, we can observe the output features in a stochastic way. So there are three groups of parameters in this input and output hidden Markov model. The first one is the distribution of the initial state. The second one is the state transition. And the third one is the emission probability, which is how likely you observe certain output features given the taxi state. So because in this study we don't have the true label, so we can only use the expectation maximization problem to estimate these parameters. And I'm sure you're very familiar with this algorithm. And in this experiment, we define the features like this. For input, we define these binary variables to indicate whether this vehicle is operating at night in a hotspot area on the highway. And the last one is an indicator of whether this vehicle is likely to have an occupancy flip. For example, it is moving at a high speed, then we think it is not likely to have a occupancy flip. And for the output features, we define define the vehicle movements based on whether it is moving at a constant speed or accelerating, decelerating, and also whether it is making a large turn and whether it is doing a stop. And the last one is just observe the transition in occupancy. So in the experiment, we first do some trajectory processing and segment them into the trajectory sequences. And for the training, we have 3,000 trajectory sequences, 10 for 200 taxis, and 10 sequences per taxi. And we split this training set into 10 batches and learn one model for each batch with multiple random initializations. And for testing, we manually labeled 115 sequences and use that for the model testing. And we also collect a small sample with a large amount of errors to test whether our model is robust. So in the model evaluation, the first task is to transfer the taxi state back to the occupancy status. So basically, we assume the occupancy flip happens at the end of pickup and drop-off interval. And because in this study, we are more interested in predicting the change in occupancy rather than just the occupancy status. So we define the accuracy as follows. So we consider a true positive case is we have a true occupancy flip that is observed in a predicted pickup or drop-off interval. And similarly, a false positive is within a predicted pickup and drop-off interval, we do not observe a true occupancy flip. And to further test the robustness, we manually added noises with a Poisson occurrence and exponential duration. So this table summarizes the main result from our experiment. So the baseline model is the one, the batch model that has the highest log likelihood, and the following three rows shows the result after we adding some arrows into the test data. So basically, the base model performs relatively well with a F1 score higher than 0.96, but after we add new arrows into the data, the performance drops a lot, especially if this mislabeled sequence is short. However, if we have strong condition imposed on this model, for example, we only add arrows when the vehicle is on highway, then the model is quite robust because on highway it's very strong indicator that the vehicle cannot change its occupancy. So this slide shows two good examples on the label correction. So in both cases, we originally have several mislabeled segments, but after the correction, we have a nice trajectory which indicate the correct trip. However, our model is not very good for more complex scenario. For instance, this is a trip extract from that highly corrupted data set, and in this case, we think the predicted occupancy in these red blocks are still problematic. And also, if we plot the distribution of trip duration, originally we have a huge amount of trip that is less than 1 minute. After correction, we fix only part of the problem. We still have a large number of unreasonably short trip. So I would say our model is not very perfect, at least for this highly corrupted data. So summary for the second part, in this case, we use a sequential representation of this individual individual behaviors, and we cast the problem as a latent state prediction given this input and output features. Again, once we have this label, if we have the true label, we can use a more flexible framework. Like in this study, we only used a very classic Hinton Markov model, but if we have true label, we can use more general graphic models. And the second, I think the second main takeaway from this study is that how we deal with the noisy and missing label in our trajectory data. If it's hard to simply filter them, or it has a serious impact on our result, like in this study, a possible way is to model is the feature rather than label. And I know I'm going out of time, so just a quick discussion on what are the challenges and main trade-off I experienced in my research. The first issue is this data sparsity. So, for example, in the first study, we already have the 10 million data points, but after we divided into the data for each taxi and further divided into each time space slot, we only have 0.2 strip for each pixel in that hunting image. And second one is how we represent the behaviors. And our main objective is to incorporate the spatial and temporal interdependence in the representation. And both studies are motivated by this. And in terms of a trade-off, I think one main trade-off is the model interpretability. So in the second study, we used a very classic statistic model, which gives us a strong interpretation on when the vehicle can flip its occupancy. But we can also model it as a neural network, like recurrent neural network. But then the model is less interpretable. But this is also related to the last point. I think the model selection is really dependent on how the main objective of that problem. If we want to recognize some behavior patterns from without any prior knowledge, we normally want to do the clustering, like in the first study. But if we just want to predict the behaviors without the need of understanding why they behave like that, perhaps we can use more flexible and powerful models, like deep learning and imitation learning. Yes, with that, I'll end this presentation. Thank you very much for listening.
So we have time for a question, maybe, from the audience, as far as possible.
Thanks very much. Oh, no, it works. Sorry. Thanks very much for that. Very interesting. So I was just thinking, do you somehow account for the traffic state that is currently happening in your transportation network? So, because I was thinking, if you focus on the speed, right, you can say if it's 0, someone might get picked up, but the taxi could just be stuck in congestion, for example, right, or waiting at a red traffic light. So how do you account for that?
So that's why we only put the stop into the output feature. So it's not as strong. It's only an indicator that the taxi is picking up a passenger, but not necessarily. So when you predict the occupancy, you need to combine all the in-taxi and the output features, the other vehicle movement to do the prediction.
Okay, thanks.
So as you realize, one interesting features of real-life conference is that it's easy to go over time, but another interesting feature is that you get real coffee outside. So we have a break until 15 past. Please enjoy this time to network, talk about what you learned, discuss with the speakers and with everybody else.